Dr. Huibo Cao is a senior staff scientist at Neutron Scattering Division at Oak Ridge National Laboratory, USA. He earned his PhD in condensed matter physics in 2007 from the Chinese Academy of Sciences, where he studied macroscopic quantum tunneling in single molecule magnets. Dr. Cao continued his research at the Léon Brilliant laboratory in France, focusing on frustrated magnetism using neutron scattering techniques. Since joining ORNL in 2009, he has primarily been responsible for the demand single crystal neutron diffractometer at the high flux isotope reactor. Recently, he has extended his expertise to the elastic diffuse scattering spectrometer Corelli at the spallation neutron source. In 2018, he was awarded the US DOE Early Career Award to Advanced Polarized Neutron Diffraction Techniques for the study of quantum materials. I'm very glad that you have accepted our invitations. I have just returned from Oak Ridge and I'm under so big impression of the site and all these instruments there. So I'm looking forward to your lecture. Huibo, the screen is yours.
Thank you, Christoph, and also thank you, Paulina. You both organized this very important QCR webinar. So, good morning, everyone, and maybe afternoon and evening. So depending where we are. So, this topic I think is compare Nicholas gave very good talk on this provide solution. So this one I think probably is. Actually, it's after talk. Probably you will say maybe I ask for solution. So that's probably complementary me. So very interesting seminar. Let me start. So the talk title will be magnetic symmetry. So this is one of the topic. So the chirality is one of the ubiquitous property, like so in many objects you can observe this, like from DNA to the spiral galaxy. So it's a if you think about our hands, that's probably most universally recognized example of chirality. We call handedness of sometimes we call chirality, right? So left hand or right handed. So our hand is a very good example to figure out what chirality means. So there no any rotation on translation symmetry. You can orient your hand. You never be able to overlap your right hand to left hand or left hand to right hand. So that's the exact definition of the chirality. So the chirality in the molecular, molecular, I think there's a lot of interesting things happen, like those spin, chiral-induced spin select effect is can connect very many like bioselection and chemical selection even. So those spin select effect is one of the important direction of the study of the I think organic, like those organic morphs or organic biology. So for example, like so those medicine is depend on chirality that can be toxic or can be effective. So it's all the importance of the chirality, but in the study we are doing with the crystallography. So it's in the crystallography, the crystal I think we have is probably not many chiral structure, especially in the inorganic small unit cell crystals. So in over like think about the space groups, among like 230 space group, only like 22 chiral space groups. That's actually represent like include like 11 enantiomorphic pairs. So that's actually in space group actually we don't have many. So here is like just show those like a pair, one of the different belong to different space group for tellurium. So you can say different chirality belong to different space group. That means actually we have like 11 pair of this kind of chiral space groups. So this is one of the magnetic version of the system. Also is I think connected to the chiral and also connected to the toroidal moment I'm going to talk today. So currently in magnetics, because I'm working on neutron, neutron is good is to detect like Nicholas already introduced, is pole neutron and the regular neutron is determine structure. Nuclear scattering determine structure, also determine magnetism. So for the chirality of magnetism, there are two mathematical definitions of it. It's one is the vector chirality, and one is scalar chirality. So vector chirality is just a two spin. You can just sum up, do this cross product. You can calculate the vector chirality. This is if you do a mirror, just play the chiral definition. If you play mirror, because the spin is axial vector, so you will its mirror will like flip like a plus to the minus. So from that chiral, there's again is also there by any rotation translation. You cannot overlap one of the object with its mirror. So that's a mirror image. So that's one of the vector chirality. For scalar chirality, is actually the non-coplanar spin structure. So this more also more connect to some topological effects. So for example, like anomalous Hall effect or thermal Hall effect. So that's the two kind of scalar chiralities related to spins. So that's more like those chirality also can trigger a lot of interest in like we call quantum state or the magnetic states. So scattering is one of the like interesting topic in the field. I think with neutron is the one of the technique to play the role. And also multifluoric has been studied for many years. So it's like a spiral spin can drive the polarization. That's can realize magnetic electric immutable control. So also recent those like a topological Hall effect, anomalous Hall effect. That's also this work is I think it's driven by this magnetic chirality. So also superconductor in chiral structure also could be in reciprocal space, not a real space, also reciprocal space because of all topological insulator Fermi surface related stuff is application to topological electronic device. So all interesting topics. So today's talk is actually here is going to today's talk is one of the chiral structure. We found some toroidal moment is kind of there's a spin chirality and the spiral the scalar chirality also have toroidal moment. So by applied field, actually we can switch by only magnetic field we can switch toroidal order. So that's may connect to those like spin selective phenomenon in the bio, but that's only in generality. But this compound is where is definitely is more focused on the more connect to multifluoric or ferrotoroidic is one of the order we will introduce later. So also including some first principle calculation. That's because that's as Nicholas mentioned, it's very important now. Is experimental and theoretical calculation is together we can understand what's going on in a system. So the last if I have time, I may quickly introduce the excitation and structure disorder. That can connect to the topic we are doing today. So I may need some method to solve those structure disorder. So a toroidal moment is a toroidal is widely used in electric component made by bending, for example, bending a solenoid into a torus. So this magnetic flux line is generated by the solenoid from a closed loop. The same principle is applied to the create powerful magnetic confinement of a host plasma in Tacoma. That's one of the, you can say this. So they can provide for powerful magnetic confinement of the hot plasma. So in solid state material, so the toroidal moment is generated by this kind of vortex. So spin is the head tail connected. You can give it a spin like spin texture. Depending on the rotation direction, you can get the plus and minus toroidal moment. This is mathematical definition. Cross product of you can connect all the spins by rotate around this vortex. So actually toroidal order is one of the four ferroic order, including like ferroelastic and ferroelectric and ferromagnetic. So ferrotoroidic is less often to say, but it's actually this is one of the ferroic order. That one is actually break both time and spatial timing reverse symmetry and in special inversion symmetry. So like ferroelectric, those are just break one of the symmetries, either spatial or time. But here is break both. So that's break for ferrotoroidic order. So the pioneer work is for the toroidic order is actually in this actually is more like collinear this triplet material is a collinear magnetic order, but there's a spin paraspin collinear. If the collide, they will not give any toroidal order, but if like a parallel, they go different way, they give the toroidal moment. So this why in this material they found is a toroidic domain. Use a second homologic generation technique, they can say this domains. For example, here you can ferrotoroidal domains, those red line, you can just circle those is ferrotoroidal domain. Different color will be the different one, the other side, so flick domain. At the same time, also you can say magnetic domain is use a different like gray, dark gray and lighter. That's a antiferromagnetic domain. So you can say they are not like overlap each other. So they are relevant. There are no any constraint between them. That's one of the property of toroidic moment, because that's required like a cross like a real space and time space inverse space. So magnetic is represent like a time inversion symmetry break, and the ferrotoroidic domain is need break both. That's why they are ferrotoroidic order actually independently is order. So by how to align the ferrotoroidic domain is what's this following paper they did the work is they apply the crossing like electric and magnetic field. They can apply this domain. You can say this are aligned. But if a magnetic field only, you will say that it's still mixed. Or electric field only is still mixed. So the required control toroidic domain is require both crossing field control. So that's like another work has to use a polar neutron, because that's also can detect like a very good technique can detect the symmetry break for both time symmetry break and the spatial inversion symmetry break. So here this actually is a combined symmetry break is use a spherical neutron parametry. They can detect this side change. Again, they apply electric field and magnetic field together, crossing field application to the material. They can by analyze the spin polarization, they can tell that's flip the domain flip change sign. Like if it's plus, and they say this, if it's flip one of the field, they can flip the domain. But flip both, like change the direction of the electric field and the magnetic field together, no flip. So that's another way you use polar neutron to confirm there's a ferromagnetic domain. It's how to do the domain control. You require cross field control. So if you apply only one field again, they don't say any domain ratio here. So that's from spherical polar neutron diffractometer. So here is another thing I want to mention is like a thing we talk about is we want to control toroidic magnetic domain. So to control this, you will require like a two ferroelectric order, just like multifluoric. We can apply magnetic field. We can switch the electric the polarization, or apply the electric field switch the magnetic domain. So this is one of the like well-known like type 2 multifluoric. It's a spiral. Again, it's a spiral. Is kind of like it's a chirality. So by apply the field, you go by apply the field, you can control the polarization, because the apply field spin rotation plane will flop to different plane. This is why polarization also can change. So it's a kind of control through this. They call it current-driven mechanism, spin current model. So that's different equation to calculate how the polarization responds to the spin rotation. So the topic of toroidic order is kind of same. So if you want to control the toroidic domain, so we also require another ferroelectric order, then we can realize the multifluoric complete control. Here is the material we are talking about today. Actually, the material I had before I introduced the material, actually one of the things before we go in there, we want to introduce is chirality again. So if that's a spin, it begins spin axial vector. So if you do mirror, that's you can say this is one of the triangle motif. So how spin light. So there's this is 3D plot. So spin go turning, give the torsion moment up and down, depend the turning direction. So what's a mirror play is you can say the flip, the spin is perpendicular to the mirror because it's an axial vector. So they will not switch direction, but the other direction are flip, obviously flip. So this is why you say this kind of rotation. Give the torsion moment is same because the rotation direction is same. But the only difference is spin up and spin down. That's actually connected to the scalar chirality. Also, you can say the plus and minus. But for the torsion moments, this mirror connected one, they don't flip the sign. Only if they stay in one side chiral configuration, the spin flip, they cause torsion moment flip. If you look at the magnetic, so if you look at magnetization outer plane, that's also you can say this outer plane is up and this outer plane is down. Moment is down, so it's up and down. So they are actually can be connected if we stay on one side. So that how it stay on side is then come to the structure itself is because the compound we will work on is a chiral structure. So that's ensure we stay one side. So that's I will focus the torsion moment and magnetization. That's the one thing we are focused today is try to use the magnetic field to switch the torsion moment. So the structure we are working on is a chiral structure. You can look this like a tetrahedral is that's cobalt oxide tetrahedral. Cobalt is staying in the oxide for oxygen, connected for oxygen is tetrahedral. Between cobalt tetrahedral is connected by the silicon oxide tetrahedral. So you can say interaction is the kind of we don't expect like very strong interaction. This why the transition temperature you can say that by stability measurement you can say the transition temperature is 3.2 K. So that's all expected. Another thing is if you look down from the c-axis, the symmetry is P63 is chiral, also polar symmetry space group. So it's a structure when we strike out by the of course by the solved solution structure solution we know is only one enantiomer. So that means only one chirality. So we don't have like a twin like a. That's also is is actually universal for most cases. Only one chirality exists for like the DNA and our like many cases there are only one enantiomer. So if you look at it from c-axis look down, you can say this tilt of each tetrahedral. You follow this red spot, the tilt direction. You can say the chirality. They are rotating. So each actually by the way also you say so we use different color to bound the different cobalt tetrahedral is based on distance. So is the near distance 5.05 angstrom is the nearest, and between the those triangles their distance slightly bigger. So we say that's kind of trimerization. So we can think about that interaction probably strongest magnetic interaction, and other can be weaker. So that's kind of by just looking at the structure, we can think about it, something we can guess. So then this compound that we run neutron first before we put on the effort on this. Actually, we know it's a chiral structure, and but we didn't. At the beginning, we didn't try to do same crystal. First experiment actually we did is powder. That's at a powder at spread neutron source. This data is that this only shows data below the transition temperature below 3.2 K. So this actual peak is that low Q is represent like a magnetic propagation vector. Those are can be indexed by propagation vector 1/3, 1/3, 0. Peak one of the reflections, temperature dependence, you can say disappear at 3.2 K. That's consistent with the stability measurement. So that's the magnetic order we're looking for. Also, that's a structural refinement to show the compound is chiral. So here are the two to simplify the view of the magnetic structure, we only plot the spin vectors. So that's still again. So one third actually is this dot this dashed line is represent the nuclear strand unit cell. So one third order actually like a three makes the unit magnetic unit cell 3 times bigger. So square root square root 3 by square root 3. That's the magnetic unit cell. The color is help us to view this magnetic structure because it looks very complicated if you lost couple same color. So if we couple different color, just each like a triangle, that's still the stronger. We expect stronger the interaction. You can say that's each triangles spin is 120 degrees away from each other. That's like one for the thing about the frustration. If you're familiar like magnetic frustration or the triangle lattice, if interaction is antiferrous, because they couldn't satisfy any of the pair of interaction, become a collinear antiferrous. This is why they give this 120-degree order. But the tilt, the usually 120-degree order is not like we don't expect this universal tilt. They give this like a chirality. But here we saw it. So that's all determined from magnetic structure neutron diffraction experiment. So what we found, if you look at different color, different lattice, you can see the collinear antiferrous is between trilattice actually is at a different layer. So then by connecting those like a lattice, we actually can get 3 sub-unit cell. So those are like a first near neighbor. We expect them interaction is strong, but because frustration, they form this 120-degree magnetic order. By interaction, you can say is that this interaction is a perfect antiferrous. So those interaction also strong, also no frustration, not much frustration there. So they can stabilize as a happy position. So by just these 2 interaction, we can make the connect the whole magnetic lattice in the crystal. So then we get a different color. So that's a structure how we understand structure when we got a magnetic. We solved by neutron diffraction. We say if it's physically makes sense. So that's a 3D plot. If we just connect all this interaction, we think the most intense interaction happened. Then we got 3 sublattice, magnetic sublattice. So the interaction between them likely is weak. But since the 3D magnetic order, some interaction need to be there. That's all the based on magnetic structure, we can get information. Another thing is we talk why we think it's a ferrite-toroidic order. So again, 3 sublattice. If you look at one of the color, the rotation is this way. Another one also rotation this way. If you remember the formula, how to calculate toroidal moments, that rotation all same direction. They are both. If we say this is minus, red one is minus. Other rotation, they rotate all blue and green, they rotate different way. So will be plus. This is why each sublattice they give a toroidal moment like 1, but there are 2 sublattices going down. Two is go up, 1 is going down. This is what we call ferrite-toroidic order. So that's based on magnetic structure pattern. We found actually there's a toroidic order in this system. So to confirm, of course, since crystallography, I think if we want to confirm its magnetic structure, those rotation is real meaningful. It's not actually not like a random. We stack some local minima. Actually, we try to define the universal spin rotation. Then we trace the rotation that tracks the refinement quality. Actually, we found all minimum actually all connect to this kind of magnetic structure. So okay, then those are like a certain position. I think that's if at 6 degree, the worst refinement quality that gives this like a spin all in or out. That's a typical like Heisenberg interaction we expect. So this kind of interaction wouldn't, is a magnetic order wouldn't give any toroidal moment. So they are cancelled. So then we can, since that's we got from a powder sample. But if you do same crystal sample, we can actually apply field on different direction. That's one of the magnetization measurements. If you apply the field out of plane along z-axis, they actually have observed the ferromagnetic moment. It's 0.1 mu b. And this is a sigma. The other moment is 3.3 3.2 μb at the 1.8K, I think. So, but the ferromagnetic order, actually the ferromagnetic moment out of plane. That means spin is not fully in plane. There is a tilt out of plane. Actually, out of plane actually the form gives some net magnetic moment. That's from back measurement. If this is interesting or not, I think we will see later. It's not from impurity because transition temperature also collected. I think it's definitely not from impurity. So by things that we did the same field measurement by applied field out on plane with single crystal with neutron and a single crystal diffractometer. So that's all we picked one of the magnetic peak at like still same magnetic peak we use for temperature dependence magnetic ordinary parameter. So you can say the based on when we change field is again field is out of plane. So this one third large unit cell magnetic order is melted, disappear is suppressed. At the same time, the k equals 0, that's 1 minus 110 is nuclear peak, but this peak is showing test increase. That means magnetic unit cell is back to the smaller unit cell from a bigger supermagnetic unit cell to a small unit cell. That's exactly the same as the nuclear structure unit cell. So what happens is for each change, if you think about that's a magnetization measurement again. So if you measure magnetization, that's a small loop is at beginning. That's just a small field. It's like this milli Tesla. So it's at a larger field region, you wouldn't see this small loop. But that's like alignment. First step is connect to the magnetic domain alignment. But you increase field further, actually another steps. That's we say the several stairs of this ferromagnetic magnetization steps, the applied field out of plane. But what happened in the neutron? What we say is the antiferro disappear, another k equals 0 magnetic structure, magnetic order shows up. But the moment size here you can say is still small. So definitely it's not into a polar neutron, not fully polarized magnetic phase. I mean, a field induced like a ferromagnetic order. That is still in antiferromagnetic order. So by the Plex data at I think 2 Tesla, we can solve the magnetic structure at this phase, 2 Tesla. So I will click the slides if you focus on this one to see what's changed. That's to the next slide. Yeah, you can say it's a blue, no change. A blue triangle spin direction stays same. A gray one also stays same. But the red color one, they switch the spin direction. So this moment, because we didn't use the polar neutron for this experiment, so those weak ferromagnetic moments we wouldn't expect like we can say by a polar neutron because on top of nuclear peak, so we wouldn't be able to say it. But the intensity changes are still. This means this character still even k equals 0 still k equals 0 antiferromagnetic order. So what happens is in play. Think about the other antiferromagnetic order is in play, but when we apply field out of play, so this change the direction. Again, follow this one. So that just spin is the in place change direction. That's actually interesting. Like we apply field and in place spin direction switch. That's once they switch, what happened? Turn moment is because that's all rotation in the same direction. From a ferrite, all become plus. So from a ferrite become ferro, toward the order. So remember here is the first step is magnetization. Another magnetization, they increase the spin, ferromagnetic component. At the same time, toward moment also from ferrite to ferro, the ferro toward order. So how to understand this compound? I think then we involve the for calculation with at the beginning we just only this DFT calculation only including like Heisenberg spin interaction. We didn't consider very complex case. I mean only collinear spin interaction included. But DFT calculation will depend on the based on bond distance. You can say which band of band like can cross the Fermi surface. We estimate that's the interaction we need to consider. this represent different distance, like a different bond. There's a bond, we expand this strong bond, interaction bond at this one. That means this G we call G trimer and GZ. Other has subleading other term like G, other interaction we didn't label here, but it's here. So there are more other interaction. So TG trimer prime, then just between trimer, not intra trimer. So we include the other interaction. Here you can say G trimer and GZ should be quite strong. Yeah, here we couldn't tell, but this is just tell this integral has some contribution. We extend all this could be strong. But let's say what's next. So that's based on a minor structure, the interaction we got from the DFT collection. By play different U as interaction, we can say GG and GZ actually is strong as we expected. And our other subleading term is actually is relatively weak, but all kind of similar amplitude. So this consistent with by DFT calculation, we confirm our structure and all consistent can be explained by the DFT calculation. And why, the question is why they form ferrite toward order, why the spin rotation happen, is give the toward order, tordic moment. That's question with this Hinsberg interaction we couldn't explain it because this only can tell 120-degree rotation, but no tilt. To include the tilt, I think we need to think about the spin direction, prefer spin direction. Once there's prefer spin direction in the plane, we need to including actual term in Hamiltonian. So now we include the Dislowski-Maria interaction, we call DM interaction. So that's an interaction that's came from symmetry. So for each bond between because the structure symmetry, crystallography symmetry, each bond have their symmetry. So by including the DM interaction, that spin can turn. That's the way that's the DM and in Hamiltonian we included. So by including DM interaction, that's actually you can say DM interaction is not if you go perpendicular to the bond, so the spin just a perfect 120 degrees, all go in or go out. There are no total moment. But the DM vector when it rotates, they can have different chirality of spin chirality. So let me DM vector also have a chirality. Symbol, the thing is the nuclear structure is chiral. So this based on symmetry, we DM vector is chiral is actually expected because it's naturally like from the crystallography. So by consider DM including DM vector, we can explain the rotation of spin. I mean the minor structure determined by neutron diffraction actually also can tell the various DM factor direction. Also tell the chirality of the DM vector. So now another thing, in-plane DM vector, we know we require in-plane DM vector that makes the spin turn. But the question why is we can flip the toward the moment on applied field out of plane. That's actually another details we need including not just in-plane DM vector, actually is a slight out of plane. So DM vector cannot just stay in plane, also need to go out of plane. So think about this, if we apply spin, there are two options. They either like a flip, spin flip, because DM vectors require their chiral. So they require this kind of universal rotation, but not like a relative 120 degree. But if you apply the field to Tesla, you can go here or go here. So, but the reality is we only get this one, spin flip, not the spin turning this way. Again, it's limited by the DM vector. That's naturally from the chirality. Think about this. They both still the same spin chirality and follow the structure chirality, but this one is actually different. So there are no mirror plate. They require mirror plate to match up each other. Otherwise, this is kind of they are different. So actually, when we apply field out plane, we switch the toward moment, but at the same time we keep the spin chirality. We didn't switch the chirality. So it's all the chirality when we apply field, they stay right-handed. So just flip spin. So that's come to the last one is like a y will plus a field out on plane. We can affect the tornado spin flip in plane. That's I just mentioned. We need another DM vectors out on plane. That's an out of demand for make spin tilt out. Then also that gives the actual ferromagnetic. Think about this rotation. If all tilt out, spin is the following same way. If all tilt out, they give that moment. If all tilt down, they give a difference. By symmetry, or actually the ferro tornado also connect to ferrite tornado also connect to ferromagnetic order. So they are connected when they flip, just like the first, before we start talk, I showed that's a table. They are connected. So that's the subleading term actually here is do further Hamiltonian calculation is y is beginning is ferrite, then ferro tornado order. That's all because subleading term. So that's based on those calculation, including field direction. We need a subleading term to make this happen. So that's both the interaction between the different sublattice. That's a stabilized ferro tornado order at zero field, and the energy prefers change after apply field. They go to the ferrotonic order. So this is I think that's we explain how things happened. They actually we couple the ferromagnetic order and ferromagnetic only auto plane ferromagnetic order to the ferrotonic order. This one we can use magnetic field switch the tornadic order from ferrite to ferro. So whereas easy play a single anisotropy come, that's a puzzling. At the beginning, with our theorists, they don't expect strong spin optical coupling because for the couples 2+ in the tetrahedral place, we perfect like a stable at E2G. So we don't expect like a strong spin optical coupling. But later, but all this interaction, if we do the magnetization measurement, go very high field, we can say saturation field actually 20 Tesla different. That means definitely strong spin optical coupling. How to explain this is that we look at each tetrahedral, actually not like perfect tetrahedral, actually the very strongly distorted. This could mix like EG to T2G orbitals, make a strong spin optical coupling. That could be reason. So this also confirmed by if do inelastic experiment, so you can see this flat band excitation. That's actually from one lower spin state to the larger spin state. That's we call stretching mode because size change involves spin size change. So now all this can be explained so far. So that's some similarity. If this actually is a similar feature also in the other cobalt material, you can see as flat band. This are consistent. This is related to stretching. They call stretching mode or the Higgs mode. So doing this is those like high energy we say those spin stretching mode. So involve like a different spin state. So if focus on low energy excitation, actually we say we didn't find a well-defined spin wave, just like other cobalt material, like spin liquid track lattice. You say well-defined spin wave, but here we don't. We only say the strong, like resonance kind of excitation around 0.3 MeV. So that's without doing modeling, that's called one of excitation is like tornado moment. Think about like we use field, we flip the tornado moment, but this could be like for each spin as a motif, triangle motif. When I do neutron excitation, actually they probably one spin flip, other two spin follow, and maybe this related like a cluster excitation. So the weak is excitation is a low energy actually, so gapless, but it is extremely weak. So this is mostly like a feature we notice is like a motif excitation, more like triangle excitation together, or maybe we can tornadic excitation, tornado moment excitations. So this the modeling, I think we are still working on it because some details we notice if we look very detailed, like lower the scale for the reciprocal space plot, like beside Bragg peak, we also see some feature about some diffuse scattering that are related. And those diffuse scattering also, you can see the structure diffuse scattering also follow chirality. There are some chirality. So the chirality, like a diffuse scattering at L, like if we plot HKL space in reciprocal space, L equals 0, we didn't say much diffuse scattering, but L equals 1, we say it. That means diffuse scattering may be related mostly like an auto plane displacement. This we did a single crystal X-ray with a structural refinement. If we only consider the Bragg peak, we notice some atom need to be split. And for diffuse scalar modeling, now we are trying to do diffuse displacement correlation, correlate those like split atoms, do the modeling, but it's still in progress. So again, so if you look at the back to the magnetic excitation, you also can say if you do the constant energy cut, you can say this the Q reciprocal space map. If you look carefully, you also can see it's a spiral feature. So it's in this chiral structure material, we see all magnetic follows. Is there some spin chirality? Also, the spin chirality involves toroidal moment, toroidal order, and the field can switch toroidal moment, toroidal order. So that's come to the summary of my talk. So we use magnetic field only to switch ferrite to ferrotic order, and interaction we combine the theoretical calculation and the experiment. We got I think reasonable explanation what happened in this system. We know how to switch the toroidal moment because once the major factor is DM interaction. The DM interaction turning DM interaction like rooted from the chiral structure. Another thing is there's ferrite magnetic order inside too. So that coupled to ferrotonic order. This why we can use magnetic field only to switch toroidal order. Same time, if of course for ferrotonic order, we can also flick domain, magnetic domain, but that's more because already crossing field we required for flick toroidal moments. This why it's not a mutual way to control. It's only one way. We use the magnetic field control the toroidal order. So there is subleading term that control Y is ferrite and ferro. And we are still working on continuous modeling magnetic excitations. That's to say those continuum is intrinsic from like a multiple magnet is more like Cantor spin effect, or is structure disorder effect. So that's all required. Like we need to do the good model of the structure solution, including not just Bragg condition, Bragg peaks, also including diffuse scattering. That's we are still working on that. So I think that's the end of my talk. And before the finish, I think I need to acknowledge the big team. The one is on the left side is the DOE team that's supported by this fund, DOE Early Career Funding. Is the postdoc. These three postdocs, they are kind of leading this work, and also two other postdocs, James and Megan, is currently working with me, and they are working on the structure solution and this manual modeling, excitation modeling. And also the instrument we use the Paojin, the local contact Qiang, and the Chirality is Feng Ye and Zach Morgan, the computation instrument scientist. High-spec also we have we use those dynamic study we measured at high-spec, and CNCS, OV and Daniel. So our senior collaboration like Sunchang's group and Xianghan group is a large crystal for also neutron work. And we also high field magnetization married Los Lemons, Vivian, Neil, and Xiaxin. We have three great theorists to make all this complicated math structure and how we explain the experimental results. Harold and Igor and Daniel. Daniel just passed away. So very, very active, very good. Our very good theorists in the field. So I think that's great to my end of the talk. Thank you.
Thank you very much for this excellent talk, which is now open for questions, for comments. You mentioned single crystals. How big crystals one should have in order to be able to get this kind of results you are presenting?
This for crystal, I think for diffraction is like a couple millimeter size crystal. Diffraction is usually millimeter, couple millimeter. But for inelastic, I think our crystal is a gram or two. I think around 2 grams for the inelastic measurement.
Okay.
Yeah, So, these are relatively large crystals. How about the defects? Probably you have some defects in your crystals. How they influence your results, or how you avoid defects?
Yeah, that's a very that's a in the whole field, even for those like believe like those paraclaw crystal, the people are looking for fluctuating magnetism. That's a it's always some side defects. That's why it's when we say continuum, you usually at the beginning people believe that's a spin or quantum speed rate, but slowly some cases it's not that easy because side disorder also can contribute to this continuum. For this crystal, definitely you see those defects, those diffuse scattering. That's all I call the defects. But the defect is chemical defects or the displacive defects, like related to like a transformation, those structure vibration. So that part is we are still working on it. This one we still believe because based on nuclear just bragg peak refinement, same to displacement defect can explain it. Bragg peak wise, but the model to those correlation between displacements, those introduce those diffuse scattering, that's kind of difficult because one reason difficult is there's some softwares like a 3D data PDF they can do it, but in often difficult because those we measure those in the sample environment, those give a background also, yeah, those are complicated data. So always background those things we cannot directly use those Fourier transformation to solve it. So there are two ways. One is a clean background, make a really high quality data. We can use 3D data PDF to solve it. Or we need to find the model user. Just think about what possible model we can play to simulate, use simulation to generate the pattern, do the pattern comparison to get the idea. So this one, yeah, we are actually working on defects. So to say is what kind of defects?
Okay. We can see on chat some advertisement. Paulina, because you go there, can you comment on the Sagamore conference a little bit now?
Yeah, so we mentioned about the Riches School, which is next year, but this year in 1 month we will have a Sagamore conference, which is a conference organized by quantum crystallography community. And yeah, we'll have many interesting invited attendees and talks. You can still register. And there will be also some short workshop, 1 day workshop after that. Yeah.
And I have learned that there will be also magnetic part during this conference, and Huibo will be attending it with and present some contribution also at the Sagamore conference.
Yeah, I'm still waiting for the pro travel pro from cover. Yeah, it's in DOE, so should be okay. But yeah, I'm still waiting. I think Xiaoping will be there definitely.
Can you also comment a little bit? I mean, not that often people collect data at Oak Ridge. Can you a little bit comment on possibilities of those instruments you were using? I mean, demand and Corelli.
Topaz,
For the
yeah.
sake of also advertisement of this experimental possibilities there.
Yeah, I think if I think most all instrument actually some parties overlap. For example, magnetic structure wise, the demand and Corelli some overlap because they can reach a very extreme sample environment or magnetic field. Topaz can reach like 5K, but the magnetic field is I think is because the instrument setup is not for that purpose. No, Topaz is, but Topaz have a very good time coverage, like wavelength coverage and detector coverage is very efficient for the structure solution, like a hydride, those like a crystallography. That's a dedicated crystallography diffractometer. And demand can do it, but not when you do data collection, it's not efficient at time flight. You can quickly collect huge few sound reflection. This one demand mostly is focused on magnetic structure and can collect full data, but it's like a very traditional full circle diffractometry. That's actually I'm from LB. That's many familiar person I saw in Nicholas' slides. So
okay.
yeah, I think it's sweet. Also, we have like a Mandy and Imagine X. They are do especially for protein crystallographer. They are now in doing the Imagine X. They are do DNP, dynamic nuclear polarization. Actually, they can change by those techniques. They can change the structure factor of hydrogen. So then if you do the spin up, spin down, you can get the contrast from hydrogen, only hydrogen. So that's something is opportunity, but they are, I think probably next year, I think they will commission it. Hopefully some very interesting thing for hydrogen related study, I think.
Yeah, and we as a users should remember that ILL is actually now closed for refurbishment. So Oak Ridge is really this rare case of excellent alternative for especially for scientists from Europe. So
yeah, that's very good. Yeah, that's very I think it's a yeah in the world we don't have many neutral facilities, so better we work together and yeah this month I think also visit Japan, so I think visit their neutron facility. I think yeah I use the Grenoble instrument like pole neutron diffractometer there, and I learned to start my neutron scattering from LLB. That's Asen Kukasov and also Sir Beatrice Raylon and also yeah. So many people yeah. So, oh wow, that's one Nicholas gave to us. Oh wow, finally some connection we made.
yeah. Well, we have a comment of Marcin Maździarz that you cannot avoid defects as voids. Yeah, that's
yeah, that's definitely true. I think one of the comment, I think we are talking about the quantum qubit things. That's one comment from I forgot who mentioned like for the material we are studying is in application wise not possible because of defects.
yeah.
So this one silicon carbon is yeah, defects one bigger, but it also can be the opportunity for the study wise. So defect also can affect the property. So depending which way we think. For fundamental science, I think we are reaching that. That's Chirality actually is very good for those study, diffuse scattering. They also this Chirality chopper they can study determine is a static or dynamic defects. Those defects can be if dynamic, then it can be spin glass or it can be the phonon, magnon. So I view that's also opportunity. So defects.
Excellent. As I do not see more questions, so thank you, Nicholas, and thank you, Huibo, for these lectures.